Hello mathematicians, we're now going to have a look at the log function and its derivative. So we're starting to look at the calculus of the log function. So we're going to be using the log function with base e, which is known as the logarithmic function, or sometimes the natural log function, and it can be written as log base e, it can be written as ln x, or sometimes it's just written as log x because it's the logarithmic function. It's also sometimes called the Naperian log function because that was the person who did a lot of work on actually getting the values for this log function. Now, sometimes, because it can be written as just log x, we need to be careful because while it's written that way in maths texts and possibly even in questions, but hopefully not, on the calculator there's a slightly different notation. So on the calculator, it's the key which is 10 to the x, which has just log written under it. So that log without a base on the calculator is actually log base 10. Whereas e to the x has ln, which is log base e. So be careful with the calculator. So the derivative of the log function, y equals log base e of x, is the reciprocal function. In other words, the derivative of y equals log base e of x is 1 on x, where e is an irrational number with an approximate value of this. Now we say an approximate value because being an irrational number, it goes on and on forever. It's a non-terminating decimal, like pi, I guess. That number e has some very significant properties and plays a pivotal role in mathematics. We'll just be touching on it, but on our OneNote there's a link to a video which talks about e and why it's inextricably linked to the calculus of log functions and the laws of growth and decay. So as far as we're concerned, however, we just need to know this fact, that d dx of log base e of x, again, may be written as just log x, is 1 on x. Don't make the mistake of thinking that therefore d dx of log of any other base of x is 1 on x. It's related to it, but there are constants involved. Now, by the chain rule, the derivative of log base e of f of x, so something a little bit more complex than just x, so some function of x, is given by this, that the differential of log base e of some function of x is the differential of that function over that function. And notice that there's no log that turns up on the other side. Students sometimes find that very difficult. They want to do something because they had a log on the other side. But that's just the way the process works. And if we look at this chain rule expanded out here, we can say that if we have y equals log base e of u, where u is some function of x, then we know that the chain rule says dy dx is dy du times du dx. So that means that dy du is 1 on u, so that was our basic definition almost, and we multiply that by du dx, and du dx of course is, if we go into this notation, it's f dashed of x. So we've got 1 on f of x multiplied by f dashed of x. And this is our go-to device for differentiating logs. So if we have a look at these questions here. First one, differentiate 3 log x. So our differential of 3 log x is going to be d dx of 3 log x. So don't forget your notation, make it make sense. And that's simply 3 times 1 on x. So in a sense we could have had that 3 sitting out here, but I don't think we have to do that. You know, for example, that if you differentiate 3x squared, then that 3 just sits there, and what you're really doing is differentiating x squared. So it's the same process here, nothing new. Our next one, the differential of log of 7x squared, then d dx, and notice that the textbook here writes log, it doesn't put an e there, but it could write that. So d dx of log of 7x squared is the differential of this function of x. So the differential of 7x squared is 14x. We put that over the original function, which is 7x squared, and then we simplify it. So we get to 2 over x. And the last one, d dx of log of ax plus b, is going to be the differential, which is just a over ax plus b. Now your textbook even puts this up as some sort of special separate equation. Don't take any notice of that, just apply the rule basically. This is where it just starts to get interesting, and I literally mean interesting, not harder. So d dx of log of x, and I'll just put a bracket around this so that we realize that what we're dealing with here is we're taking the log of a function of x. The function just happens to be log of x. So when we differentiate this part, what we would set as equal to u if we wanted to do the full setting out would be 1 on x, and we put it over log of x. Those of you who like to do it by saying let u equal log of x, therefore du dx is 1 on x, therefore dy dx, where y equals log of x, is dy du dx. So dy du is 1 on log of x, and we multiply that by du dx, which is 1 on x, and we get that. This top line, of course, is written most nicely like that. And then we get to this one here, and we just have to be picking up the pattern that what we're dealing with here is a product. We've got an x cubed multiplied by log x, and we have a product rule which says put down the first, differentiate the second, plus put down the second, and differentiate the first, and then we tidy that up. So this will become an x squared plus 3x squared log x. I guess you could argue, I wouldn't be concerned whether you did it or not, that is x squared outside of 1 plus 3 log x, just so you know you've got that option. So let's have a look at this set of curves before we move on. So here we have our curve of log base 2 of x. Get that off there. Log base 2 of x. We've got our curve of log base 10 of x, this blue one, and we've got our curve of log base e of x, this red one here. As we'd expect, they all pass through 1, 0. You can see that they have different slopes. You might be able to draw a conclusion about, as the base gets bigger, what happens to the slope once you get past the point of intersection with the graph. And I'm just going to click on this hyperlink to take us to GeoGebra, because there's a very interesting fact which you probably should know, and that is that if we move this point here, so this is a point on the curve log base e of x, and that's a tangent that's drawn next to it, then if we can move that point, if I that point down to x equals 1, we can see that the slope of the log curve is also 1. So that fits from our definition of the derivative, that d dx, the slope of the curve, is 1 on x, so 1 on 1 is the slope of our curve. And likewise, if we moved it out here to 2, and it's going to get all harder to see, but when x equals 2, the slope of that line is a half. When we get out here to x equals 6, the slope of that line will be 1 on 6, and so on. And it's the only curve which has that particular property. For the others, you can see that their slope would be slightly different at all points. So, continuing on, well, as we said, while all these log curves pass through 1, 0, only the curve of log x, the natural log curve, has a slope of 1 at this point. And for the other curves, it's 1 on log base a of x. We'll come back to that later on when we do logs down the track. And so let's have a look at these examples. So our first one here is no real problem. It's the differential of 4 plus x squared, which is 2x. over 4 plus x squared. For our next one, it could be a bit of an algebraic nightmare, because we can see that we've got log of this thing, which is a quotient. So we could differentiate that quotient, put it over that quotient, and work the algebra after that. Good luck with that. Or we could say, well, we have log of a quotient, so we know that log of a divided by b is log of a minus log of b. And all of a sudden, that's a lot simpler proposition to take the differential of than what we had before. So we can now just say, well, the differential of this part of our expression is the differential of 1 plus x squared over 1 plus x squared, and our minus, and the differential of this bit is minus 2x, so that changes that to a plus, and that's over, nearly got carried away, 1 minus x squared, and that would be okay to leave it in that form, just there. Now our last one is interesting. This was the point which was alluded to on the graph a moment ago, that if we have y equals that, so we want to take d dy of log base b of x, then we don't have a rule for differentiating log base b of x. The only rule we've encountered so far is the one for differentiating log base e. So what we do is change the base. We use our change of base rule, and this becomes the differential of, and I'm going to change it to log base e, and I'll just write ln, just to be different. So that's ln of x over ln of b, so log base e of x over log base e of b. And so, sorry, I shouldn't be writing that, so what I should have is that dy of that equals dy of that. I haven't yet differentiated, I've just changed the base. So when I go to differentiate this thing here, log base e of b is just a number. We punch it into our calculator if we knew the value of b. So I'm going to take that out as the constant, 1 on log base b, and then I'm going to differentiate log of x according to my usual rule, and that becomes 1 on x. So we've got 1 on log base b times 1 on x. And that is the form of our differentiation for any other base log. So if we were differentiating log base 2 of x, it would be 1 on log base e of 2 times 1 on x. Log base 10 of x would be 1 on log base e of 10 times 1 on x. So we have this constant, which is just complicating things a little bit. And if you watched that video that I spoke about, you'll remember that they said that the elimination of this constant is one of the big reasons for doing most of our calculus with log base e. So next thing I want you to do is play with differentiating log base e with these questions here. Remember, everything you know about differentiation so far is still is still applicable, but now we've discovered how to differentiate a new type of function. And what do we use the differential for? Same as ever, finding slopes, therefore getting equations of tangents, etc.